Now here's what I suggest. Close your homework and set it aside. And let's get back to these 4 addition reactions. And because we got as far as telling you there are 4 addition reactions. And as far as telling you there are 4 different reactants. And then I told you that 2 of them are symmetrical and 2 of them are unsymmetrical, yes? Mm-hmm. Okay, but I don't think we got far enough to say why that matters, whether it's a symmetrical or an unsymmetrical. We might have just touched on it. So let's get to that, and then that will clarify probably your last page of your homework. Let's see, what did I do? All right, so yeah, here's where we left off, right here. So let's get ourselves a new slide. This will review for us. Here is the general reaction for the addition of a molecule across a double bond. We got this AB molecule. It's representing, it could be hydrogen, it could be bromine, it could be water, it could be hydrogen bromide. But the general thing that's happening is that half of the molecule goes on one carbon, the other half goes on the other carbon. You eliminate the double bond, it becomes saturated. You do not break that other bond there. Now what's the significance of that? Wherever the double bond is where this reactant is going to add to the molecule. So if you give me a molecule here and the bromines end up on these middle carbons, you did something wrong. They can't end up here. They have to end up here, where the double bond was to begin with. Because that's where the bromine or the hydrogen, obviously hydrogen we can't tell because it's going to have hydrogens all over it. But if it were bromine and you put one of them here and one of them on this carbon, I'd say, no, that's not going to happen. One goes on one carbon, the other bromine goes on the other carbon. That was in the double bond to begin with. All right? And if you think this stuff's trivial, if you go off to a pharmaceutical company and they're trying to make a certain drug and they need a chlorine in a certain spot, they have to get a certain starting material to get there. You follow me? They have to know where this bromine is going to end up, or chlorine, or whatever it is they want on their pharmaceutical drug. Okay, so here I said there are 2 symmetrical reactants, hydrogen and the halogen. And remember, the halogen could also be fluorine or iodine. We use the general formula X2 for a halogen. And then we have two situations where you can have an unsymmetrical reactant, or I think I called them non-symmetrical, where it's either a hydrohalogen, or it's water. And just think of this, water, don't worry about all this other stuff. These are the catalysts involved in it. If you think of water, that's H2O. Half of the molecule is an H, the other half of the molecule is an OH. It's an unsymmetrical molecule, just like HCl is, just like HF is. There's an H and something else. Okay. Now I'm going to assume we kind of understand that when you react alkene with a symmetrical reactant, you get the same thing on both carbons, whether it's a hydrogen on each carbon or a halogen on each carbon. But let's work our way through this again. Let's say we have, let me put this molecule down here. Here is propene. And we're going to look at the hydration. If I said draw out the reaction of the hydration of propene Major product only. Okay, so let's figure out what do I mean by that. So I could have a situation where here's my water. So look up on top. So the water can come along here. Let's just move this hydrogen out of the way here for a second so that you can see what would happen. So if I went this direction, I'm going to get an OH right here and a hydrogen right there. All right, this OH is going to add to this carbon. This hydrogen is going to add to this carbon. It's going to break that bond, and we're going to have. I'm going to just put dashes right there, or bonds, just so that you can see where the water came from, or where the water went.
So the minor product would be the opposite way, with the H where the OH is?
Yeah, let's do the minor product. So the minor product would be if the water molecule approached this molecule this way, the OH coming at the carbon on the end, and the hydrogen coming at the carbon in the middle. And what do we get in that case? We get a hydrogen here, and we get the OH here. And this is chapter 12. We'll learn how to name alcohols. The top one is 2-propanol. Don't worry about it right now. It's just 2-propanol. The bottom one is 1-propanol. So let's put our dashes on this one. Okay, do you see that those are two different molecules? There's no way to pick this one up and superimpose it on that molecule. This is the minor product, and this is the major product. Okay, I'm not going to hold you responsible for explaining why that's the major one. Let me tell you about Markonikov. Markonikov got interested in this. He was hydrating alkenes. And when he was first doing this, late 1800s, when he's first doing this, he could see he was getting two products. And he was thinking, yeah, maybe half the time I get that product, half the time I get that product. I mean, I could see where the water molecule half the time might come in this way, half the time it might come in that way. And so I get 50% this, 50% that. He did it. He distilled it. He separated them out, distilled them. He goes, whoa, I got about 85% that product and 15% this product. Markonikov did not know why. This is what we call an empirical observation. He didn't write up a paper and said I got 50% of each. He said empirically this is what happened. I got 85% of that one, 15% of that one. Why, Markonikov? I don't know. I don't know why. It's kind of weird. So he went and hydrated something else. He went and hydrated 1-butene. So here's 1-butene. He goes off, and what does he find? Same deal. The OH goes on the second carbon. OH 85% of the time, 85 to 95% of the time. That's the major product. Okay. I'm going to do pentene. What happens? Same thing. 85, greater than 85% of the time, he gets a product that has the OH on the second carbon. You with me? It's going, and 15% of the time, the OH is on the end. It's like the OH prefers to be on the second carbon. It doesn't like to be on the first carbon.
When the OH is in the middle, on the middle carbons or the second carbon, that's going to be the major, and then when it's minor, it's going to be on the outside carbon.
Okay, here, you need a better rule, and it's Markonikov's rule. Markonikov. So he observed this over and over and over again, just kept doing it and saying, what's happening here? And he came up with a rule, Markonikov's rule, that said the hydrogen, this is to predict the major product. Predict. Does this work 100% of the time? No. Does it predict it 95% of the time? Probably yes. All right, so this is no law. This isn't the law of gravity that if I let go of this, it's going to hit the floor 100% of the time. This is Markonikov's rule. It's a very good rule of thumb. You know, like don't buy a car on Monday that was built on Monday. Okay, that's not a law. It's a rule of thumb. All right, so this is a rule of thumb. The hydrogen will go on the carbon with the most hydrogens. And the OH goes on the other carbon. So don't worry about where the OH goes. Worry about where the hydrogen is going to go. And keep in mind that on these unsymmetrical molecules, there's always a hydrogen. And Markonikov's rule applies to all of these unsymmetrical molecules. The hydrogen goes on the carbon with the most hydrogens. The other part of the molecule, whether it's a hydroxyl, a fluoride, chloride, or chlorobromo, iodo, goes on the other carbon. So, yeah, that's what I'm saying right there. That's what I'm showing you right there. It's the same for all of these. The hydrogen is going to go on the carbon. I know you have your head down, you're doing your notes, but that's it. It's the same for all of those, whether it's water or hydrohalogenation. Okay, so you could see how with these one butene, one pentene, one hexene, it's just kind of going like that. So let me give you a molecule. Let's get over to a different slide. Here's where it's coming in. There's the halogenation. Now here's the situation with propene. I drew it out a minute ago. There it is on a slide. And it's showing you that this is the major product. The OH is on the middle carbon. By the way, that right there is rubbing alcohol. Now you know why it's so cheap. When you hydrate, the hydration of one propene or of propene gives you rubbing alcohol 85% of the time. And the minor product is 1-propanol. So 1-propanol will probably sell for more because it's harder to make. You don't get as much of it. If someone really needs that alcohol, they're going to pay a little bit more money for it. You can go into Walgreens and get a bottle of rubbing alcohol, isopropyl alcohol, very inexpensively. And then there's Markonikov's rule. Here it is applying, instead of water right here, I got hydrogen bromide. Hydrogen goes to the carbon. This carbon has 2 hydrogens on it, so it gets the hydrogen. This carbon only has 1 hydrogen on it, it gets the bromine. See, here's your major product. Okay, now let me give you one. Let's take this molecule here. It should say, the homework should say, it says just draw the major product of this reaction. And that's probably what I would do on a test. I wouldn't have you drawing both products, just draw the major product. So you have to be able to predict the major product. Okay. Now, give me the major product the reaction of water with that molecule. What is going to be the major product? Go ahead and draw it. Draw out the major product. There's a double bond there. An OH can go on either one of those carbons. Where is it going to prefer, where will it end up in the major product? Use Markonikov's rule. Okay, where do we think the OH will go? Here's carbon number 1, 2, 3, 4, 5. Is it going to go on? It's going to go on 2 or 3, right? It's the only two choices. It's going to go on 3. Why?
Because there's no hydrogens on.
0. How many hydrogens? 0. How many hydrogens? 1. So who gets the hydrogen?
Number 2.
Number 2 gets the hydrogen. Only has 1 hydrogen, but so.
So it has to be on the exact carbon. Because I was thinking of the other one. Because of
So this hydrogen is going to go on that carbon. There is 1 hydrogen there. That is 1 more. That's what's on the next carbon. So the major product is going to be this. Yes. That double bond is gone in the product. This bond does not break. This bond does not break. 1 double bond has to donate the electrons to help form these new bonds. That's where these electrons went. They went down into here. These 2 electrons went down into here. And these 2 electrons went up into there to form these 2 new bonds.
So you're saying there's no methyl group on it and there's just, a double bond. Does it matter which one is on it?
No. No, if there was no methyl group there, let's say 2-butene. Just take something simple. 2-butene or even 2 pentene. Let's do 2 pentene. We got 1 hydrogen, and I think there actually is one like this on the homework. And it's probably going to be 50-50 in that case because each carbon has a hydrogen. We'd have to go do that experiment and get the product, and we might find 55% of one and 45% of the other one. My guess is a little bit more of it would go, but don't worry about it. Just when there's the same number of hydrogens, there's no definitive major product. All right. Okay, don't worry about this. We won't worry too much about the hydration of alkenes, alkynes, and this enol rearrangement that can happen. So don't worry about that reaction. I think the answers are on the next slide here. I'm not going to dwell on it, but here's hydrogenation. Here is halogenation and or bromination, hydration, hydrohalogenation. All right, so we don't have to worry about major and minor products over here because these are symmetrical reactants. So just a hydrogen goes on each one of these. Over here, we have to worry about major and minor products. So if we said predict the major product. Okay, Where the OH going to go here on this molecule?
On the second one?
On the second one, it has the methyl because there's no hydrogen, and the hydrogen would go here. Okay, here is this thing. Now, when we talk about hydrogens, we're just concerned about here. Don't worry about what's behind here. Just worry about what's on these two carbons in the way of hydrogens. So where is this hydrogen going to go? Here or here? Right there on the end. And we're going to get the chlorine on the second carbon. Okay?
So A is hydration.
Yeah. No, A is hydrogenation. Hydrogenation. Look at, in the word hydrogenation is the word hydrogen. So if you want to pronounce it hydrogenation, to nail it down, this is hydration.
It's hydration because it has water.
Right. It's another word for water.
And then C is halogenation.
C is halogenation, and D is hydrohalogenation.
I thought you said C was bromation.
That is, it is bromination, but bromine is a halogen. So halogenation is the general term for whenever you're adding a halogen. If the reaction said complete the bromination reaction, it'd be a halogenation reaction, but you're using bromine as the reactant.
Specifying.
Right, it's specifying the halogen. Question?
Yes, so whenever you're doing this, you said the hydrogen goes to the one that already has the most hydrogen? Okay, just one.
Yeah, that's Markonikov's rule. One of my students says, summed it up this way. He must have been an economics major. The rich get richer.
What was number D again?
The rich get richer. So the carbon that has the most hydrogen gets more hydrogen. And the other carbon gets the leftovers. But in this case, the leftovers is really the prime of the prime stuff. You know, it's the OH group. So let that guy with all those hydrogens have some more. Okay. These are the products of those reactions. Okay, I'll tell you what. I don't think I'm ever going to get your attention until you finish your homework. So I'll collect the homework at 10 till. 10 till. I'll give you about 5 minutes. Finish the homework. And then we'll take 25 minutes to finish 11 and hopefully start 12. And bring your homework up here. Hey, folks, it may not be perfect. You may miss a point. I know you don't want to miss a point. But do the best you can in everything you've heard. Yeah, I think so. Yeah. It's amazing. So you don't have to worry about all this. 3-methyl-1 butane. Yeah. And that one has 2 hydrogens, and that one has 1. Right. You don't have to name it. Folks, on number 4, you don't need to name the alcohol. You don't even know how to name the alcohols yet, or at least I haven't told you. You might know. You don't need to name it.
Are these the correct instructions? Like what based on our notes?
Yeah. You're right.
Okay, I just want to make sure. It's like, does it matter that the one is touching that line, or do I need to have it not touching?
No, I'd like it all connected. Just like you would do alkane, where you continue signs on a dashed line.
Okay, because when you're drawing them, sometimes they're not connected. I'm like, are we there?
That one.
See, like this
Don't
one?
go by this.
And this is not connected, so I'm like,
Oh, it doesn't matter. It doesn't matter.
Okay, so I'm like, do these now?
I wouldn't want it kind of like that. To get it down into at least one of the lines. Or both
Yeah, I have
lines.
both lines.
That's fine.
Okay. I just want to make sure.
And you got it on the right side.
Here.